right? If I draw an arbitrary function, this case we have 10 volume averages, but if we have periodic boundary condition, then the left interface is actually exactly the same as the right interface. But if we have non-periodic boundary condition, then the left interface is actually distinct from the rightmost interface. And we have 11 interfaces, n+1 interfaces, as opposed to n, right? So the impact to the code we are writing is that now I think we have to track for more than n interfaces. So U interface, now we shouldn't just call left because we need to track both left and right, right? So this would be something with n+1 values. So on the right would be, on the right of all these would be U, and whatever boundary condition you might specify on the right. And in this case, we know we are not going to be using this boundary condition on the right, but we are going to put a 0 there just for the code to run. And my interface now has n+1 values. What lies on the left of these n+1 values is the boundary condition and the U. Okay, agreed. So I'm just going to say U plus what lies on the right of the domain. Okay, and this is what lies on the left of the domain and U. Any question here? Okay, I'm just going to say the U interface average is equal to that. And oh, by the way, in order to make the U interface average to be correct, I actually want to make the what lies to the right of the domain as actually U on the rightmost, so that when I take the average, it's actually U at the rightmost. Okay, and my U at the interface is going to be, I'll just get rid of the L here, because we now have n+1 values. It's not just biased towards the left. And the F interface would be U interface squared divided by 2. Now, what's generic for all finite volume schemes with a boundary would be UF interface from 2 to end. Oh no, on the left, that's 1 to n minus 1 minus F interface from 2 to end divided by delta x. All right, any questions? So now let's run it, right? So this is basically the difference between the left and the right fluxes. So if we run it, the code with boundary conditions, let's initialize this and run this. I think we get a dimension of arrays. Oh, I think I should be using semicolon instead, right? Let's run this again. Okay, so now we can see the boundary condition being effective over here. It's basically keeping the value to be 2, right? As the solution moves towards the right and the downsloping slope actually steepens and the upsloping slope becomes more gentle. So a shockwave is going to be formed as it exits the right domain, because there is no periodicity. It's not coming back from the left. All right, this would be basically how a boundary condition would be implemented in finite volume code. And so this is what we are going to be discussing for today. And next lecture, we are going to be discussing how a finite volume scheme can be applied to a system of differential equations, which can also develop a more complex form of shockwaves, and how it can be applied to more than one dimension, to 2-dimensional problems and the 3-dimensional problems. All right, I will see you next time. Before I leave, I want to answer any questions you might have.
Hey, Chi-Chi. Is the next lecture going to be the Monday after spring break?
Yeah, so yes, it'll be the Monday after spring break. We originally scheduled the lecture tomorrow, but I want to reschedule that because the situation is pretty chaotic right now, and I want to give you more time to respond to this emergency. So let's actually reschedule the lecture tomorrow. So we'll meet next time Monday after spring break. All right.
Okay, thank you.
Yeah. Any other questions? All right. So keep safe, and I'll talk to you again after spring break. Yeah. Bye.
Thank you.
Mm-hmm.
Thank you.